In this lesson, we will explore rigid transformations. There are three types of rigid transformations: a translation or a slide, a reflection, which is a flip, or a rotation, which is a turn. Let's start with the translation, given to us in symbolic form. Capital T means we're translating any point in our pre-image with coordinates x, y, maps to x plus 3, y minus 7. Now, to interpret this rule, you want to remember the x-axis goes horizontally. Positive end of the x-axis is here, negative end is to the left. The y-axis goes vertically. Positive is up, negative is down. So if I translate a point with coordinates x, y to x plus 3, that means 3 to the right. Y minus 7 means 7 down. So this triangle is going to be translated or shifted or slid 3 units to the right, 7 down. So now let's take a look at any vertex. I'll pick this point right here. And I want to go picture moving this vertex 3 units to the right, because that's my x plus 3, and then 7 units down. So this pre-image point up here is going to be relocated after the translation down here. This was my pre-image before the translation. This is the image after. And we know that these two figures are congruent because it's a rigid transformation. And when we are translating something, we didn't even change the orientation of this shape. It was pointing up before the translation. It's still pointing in the same direction after the translation. Let's take another example. This translation rule is x, y maps to x minus 8, y. So when we think about x mapping to x minus 8, that means I want to shift 8 units to the left. Y maps to y means don't shift it up or down at all. So we want to take this triangle and shift the triangle 8 units to the left. And once again, I'm going to take a look at any vertex. I'll pick this lower left corner, and I want to visualize moving it 8 units to the left. So there's 2 units plus 6 more. This point is going to be dragged and moved over right there. And I didn't shift it up or down at all. My pre-image and my image, and you'll notice that triangle has been shifted 8 units to the left. Now we're going to look at a reflection. We're reflecting this triangle across the x-axis. I want you to picture folding this coordinate plane with the triangle on it, folding it right over the x-axis. This pre-image triangle is currently, you can think of it as pointing up. After the reflection, it will point down. This vertex with coordinates -4, 5, after the reflection will be -4, -5. These two vertices, which were on the x-axis before the reflection, will remain on the x-axis after the reflection. And so our image triangle after the reflection will look like this. And once again, the pre-image and the image triangles are congruent because a reflection is a rigid transformation. We'll look at another reflection. This time we're reflecting across a line x equals -3. Now this is a special case line. It is a line where every single point that lies on this line has an x coordinate of -3. So think of any point with an x coordinate of -3. -3, 2. -3, 1. -3, -2. So this line is a vertical line passing through the x-axis at -3. This is my line of reflection. So when I reflect this semicircle across that line, the reflection, the image, is going to land on this side of the line. If this part of the semicircle was 1 unit away from that line of reflection, then the image will be 1 unit away. Once again, the pre-image and the image are congruent. Another reflection, this time across a line with a slope of 1 passing through the origin. This line has the equation y equals x because every single point that lies on that line has the same x and y coordinate. So this point right here has coordinates 5, 5, 2, 2, etc. Okay, now when we reflect a figure across that line, kind of imagine going diagonally, right? Every pre-image point is the same distance away, diagonal distance away from that line of reflection as the image. Moving on to rotations. When we talk about rotations, we need a center. In this case, it's going to be the origin. Picture a thumbtack, placing a thumbtack right here. We're going to spin our coordinate plane however many degrees and in whatever direction the description gives. So it's 90 degrees clockwise. Clockwise is like this, and 90 degrees is a quarter turn. So we can visualize moving the entire coordinate plane, right, with that pre-image. Where will the pre-image land after that 90-degree clockwise rotation? It'll land right here, and that is your image. Rotating a triangle 180-degree clockwise, this time picture when I go 90-degree clockwise, it'll land here, the triangle will, and then the triangle will land over here. And how will it be positioned? Try to visualize it. Here's your 90-degree clockwise and then your 180-degree clockwise. So directly across, if the pre-image was in quadrant 1, the image will be in quadrant 3 when it's a 180-degree rotation. Now the question is posed, is clockwise 180 degrees the same as 180-degree counterclockwise? Well, let's check it out and see. We did 180-degree clockwise rotation. Let's try counterclockwise. There's 90, and there's 180-degree counterclockwise. So this would be a yes. 180-degree clockwise and counterclockwise will land you in the same position. And our last example is a 270-degree counterclockwise rotation about the origin. So again, I have a thumbtack here. I want to go counterclockwise this time. 3 quarter turns in the counterclockwise direction. And let's see where we land. We started off in quadrant 1. There's my first 90-degree counterclockwise. Now I'm at 180-degree counterclockwise. And here's 270-degree counterclockwise. So my image will land right here after 270 counterclockwise. Well, could I have done a clockwise rotation to land me here? I think you can visualize just 1 quarter turn, right? So let me bring us back to where we started from. And let's try 1 quarter turn in a clockwise direction. So 270 counterclockwise is the same thing as 90 degrees clockwise.